So we're going to cover Lycor 6400. In front of you, you have some propaganda. Don't worry about reading that now. That's just for your own edification. If you want to look at it later, if you don't want it, leave it on the tables. We'll take it back, hand it out somewhere else. We're going to talk about how gas exchange instruments, specifically the 6400, but gas exchange instruments in general operate. Its principle we're going to be talking about is infrared radiation measurements. We're not going to be doing things like mass spec and some of those other techniques that you can use to get gas exchange measurements. And so what we have in front of you is a rather sophisticated heat source. That's all these things are. We're talking about infrared radiation and a detector to measure the heat. That is the sum total of it, and a bunch of electronics to support what you're working with. And so, Shannon, did you get introduced while I was outside at some point? Okay, so Shannon Loriot is head of tech support at Lycor. She's been there for 10 years, 12 years, 16 years, 20 years, I don't know. She's been there a very long time. Shannon has probably one of the largest skill sets with the 6400. If you work with a 6400 and have had a problem, the chances are you have talked to Shannon. I started as a student and I talked to Shannon. Mind you, I was an older student. I went back to school for a while. But I talked to Shannon, and I didn't annoy her enough that they actually went ahead and hired me. I tell people I work for a toy company. We make really, really cool toys. And that's what, if you think about these instruments, they really are something that enables people to do something fun. I like science. I hope you all like science and doing science. And that's what this is. This is just simply an enabler for you to do your science. And so a little bit about me. I'm a scientist there. My job is to interpret the science that you guys do for engineers. Engineers don't understand what an ACI curve is. For those of you that don't know, we'll do those. That's photosynthesis over the intercellular CO2 concentration. And so I interpret the science that you do for engineers so they can make an instrument to let you do your science. So I've got this really nice interface job, and most of my work is actually in research and development, working with these instruments and new instruments on how to make the science that you guys do better. And that's most of what Shannon and I do. She does a little bit more with ensuring that when you have a problem, and they are mechanical devices and they do occasionally have problems, that you get that problem resolved very quickly so you can get back to the science that you're doing. So we're going to jump right into this. Hopefully this is not new to anybody. Global carbon cycle, we're talking about fluxes. We're going to spend the rest of the next 2 weeks, you're going to hear about fluxes, fluxes, fluxes. This is why we build instruments. We build instruments that work at the plant level. We build instruments that work at the soil level. We have water instruments. We have atmospheric instruments. And that's what we do. We're interested in the carbon cycle within the ecosystems. So how is vegetation measured? Ideally, if you're trying to do modeling, you want to get as big a sample as you can. It'd be great if you put a great big box around a big tree and make a measurement of what that tree's doing. Put a big box on the soil down here, make another measurement. Big boxes like that have a lot of limitations. There's a lot of issues with that. And there are techniques, eddy flux, that allow you to make estimates of not a tree, but a bunch of trees. You can make some soil measurements and sort of scale that out to make some estimates of what's coming out of the soil. You can also make measurements at the leaf level. And that's what we're going to talk about today. We're working at the leaf level. That is the interface between the atmosphere and the plant. The stem, the bowl, the rest of that, not so much. There is a little gas exchange that occurs there, but right there at the leaf level is where the gas exchange occurs. Stomata. Those are the interface between a leaf and the atmosphere. The cuticle provides a very strong barrier to any gas exchange in or out of the leaf. They function that way. It's basically a bag that holds the water, and you want to control the water loss. The water loss happens through the stomata. And hopefully most of you know this. This is just a refresher. Make sure we're all on the same page before we dive into the fairly deep stuff, starting here. So think back to when you were doing basic physics and Ohm's law. So you have a current, you have a driving force, an electrical potential difference. You have your voltage. And then you have a resistance. There's a certain resistance of to those electrons passing through. Different things have different levels of resistance. And then your current, your I, which is the driving force. Sorry, not the driving force, that's the current, that's the flow through. And if you think about that Ohm's law analogy, take this and think, now you start thinking about flux. And so you have a resistance and a driving force and a different, I keep doing that. You have a driving force, which is a delta in energy in an Ohm's law. If you think about gases, a gradient in gases, you have a high gas and a low gas, and there's a gradient between those two. You have a driving force between those two. And then the I is your flux. That can be a flux. It's a movement of electrons in Ohm's law. It's a movement of electrons through whatever you're looking at. If you're thinking about gases, now you're talking about a movement of gases through a plane or an area. And so when you look at a leaf, what are the resistances? Anyone know what the resistances are in a leaf? So let's talk about water. We have some resistances that build up. I'm going to hit 3 of them here. We have a resistance to water moving out of a cell. You have a cell right here, and there's a resistance to that water moving across the plasmalemma, across the cell wall, and into the apoplastic volume. You have the apoplastic volume here, and there's a resistance to that water molecule that's now left the cell. It's got to move through that apoplastic volume, and there's a resistance to that molecule moving through that airspace. You've got the resistance of the stomata, and that water molecule now has to transfer through that open stomata, and the size of that aperture impacts how much resistance there is to that water molecule moving through. And then that water molecule moves out of the leaf into the atmosphere through a layer of still air called the boundary layer. And that boundary layer provides another layer of resistance to that water molecule moving out of the leaf. There's also a really big, a lot of resistance at the cuticle, the epidermis of the leaf. And there is a very, very, very small amount of water that does pass through that. For most models, that's actually negligible. Interestingly, all those resistances go in the other direction for CO2. Water comes out the pathway, the CO2 goes in the pathway, and those resistances are all working on both the CO2 going into the leaf and water coming out of the leaf. Now, does anyone remember about resistances and conductances, going back to the electrical analogy? Can you add conductance? No. You can add resistances. So the nice thing is resistances are additive and conductances are not. What's the difference between the two is simply a reciprocal. So the conductance is the reciprocal of the resistance. Okay, so when we talk about resistances, we really are talking about the reciprocal of the conductance. Resistances are nice because you can add them up. We can add up what is the resistance of the water coming out of the mesophyll, through the apoplastic volume, through the stomata, through the boundary layer, and get what is the total conductance to water. I'll show you in a little bit why that's important, but the thing to know is that we add up all of these. This one has a name right here called mesophyll conductance. This one has stomatal conductance, if you think of the reciprocals, and boundary layer conductance. So we can partition those out. If we know what the total is, we can start making some partitions to what are those conductances. And so what's driving that movement? Why are molecules inside the leaf, water molecules moving out to the atmosphere, and why are CO2 molecules in the atmosphere moving into the plant? What's driving that? Exactly. It's the differences in the concentration. And that's all that's driving this. So we have inside a leaf, we have a lot of water. We have cells that are completely water. This water is translocated across the plasmalemma, saturates the cell wall, and that cell wall then evaporates that water into the apoplastic airspace. Those are the airspaces between the cells within a leaf. And that airspace is saturated. It's 100% relative humidity at that temperature. As temperature goes up, the water evaporates more and keeps that airspace saturated with water. So inside the leaf is 100% relative humidity. What is it outside? Well, that varies a lot. Up in the mountains here, we're probably somewhere in the 20s to 30% relative humidity. And just to touch on it again, that's why Russ says drink lots and lots of water, because you will be losing lots and lots of water. And that's the same thing that happens to the plants. They have a gradient that build up from 100% relative humidity to whatever the atmosphere is. And so water moves down that gradient. The rate at which it moves down that gradient is the flux. Same thing happens with CO2. We have a large CO2 concentration outside the leaf and a smaller one inside. Hopefully everyone knows why we have a smaller concentration inside the leaf. It's being utilized in photosynthesis, and so the concentration inside the leaf is actually smaller than what is the concentration outside the leaf. So, Fick's first law of diffusion. We kind of started with that analogy where we talked about Ohm's law and the driving force and the current and the resistance. Well, we actually had the same thing here. Here's Fick's first law of diffusion. You can simplify that and talk about the flux, the J, is equal to the conductance. Remember I talked about conductance, resistance? We're talking about conductance now. And a concentration gradient. That's all a flux is. So a flux is a movement driven by a difference and a rate of how fast it moves. And so if you have a lot of movement and a small gradient, you can have the same flux as something that has a huge gradient and a very small movement. Okay, so we're talking very simple math. This is math I understand. So it's pretty straightforward. But this is what we're going to be talking about as far as flux. Now, it's not always as straightforward as this. So if you talk about this leaf and then a leaf that's the size of my finger, they're going to give you two different fluxes for the entire leaf. So for plants, we choose the easy. We're going to normalize these to leaf areas. So this whole flux gets divided by a leaf area. Okay? But there needs to be some sort of normalizing factor. And so what we're looking at here is, for CO2 and water, photosynthesis, A. Anyone know why A? Shout it out. Assimilation. Took me a little while to figure that one out. But A is for assimilation, is the difference between the CO2 concentration outside the leaf in the atmosphere and the CO2 concentration. We're going to simplify this and talk about the intercellular CO2 concentration. Really, you want to talk about what is the CO2 concentration right at the site of the chloroplast, but that's a little harder to calculate. We're going to ignore that and assume that the intercellular CO2 concentration is the CO2 concentration at the chloroplast, and just know that they are slightly different. And the conductance. So this looks just like Fick's law of diffusion. We have flux, concentration gradient, and the movement through the current. Same thing for transpiration. Transpiration is simply water flux. So evapotranspiration, E, the driving force, the gradient and the current, or the movement through the conductance. And so here's where, just to reiterate, there's that total resistance, boundary layer, stomatal, cuticular, and that's not right. Just what Paul and I were talking about. So we have boundary layer. These two should be in parentheses. So stomatal and cuticular, because they're working in parallel. And so you have to, their stomatal resistance plus cuticular over the total of those two. And that's the movement of the resistances through the system, from inside the leaf to the atmosphere. Now, what we do in the 6400 is we actually work to get rid of these things. So we know through measurements and engineering what the boundary layer resistance is. And the reason that's important to know is you want to know what that is, and you can calculate what the rest are. The other one is, I said that typically the mesophyll conductance is negligible, ignored. That's why you can make the assumption that the intercellular CO2 concentration and the CO2 concentration at the chloroplast are the same. That's been the assumption for many, many years. Turns out that's probably not a strong assumption. There's a lot of indication that that's not really the case. So going forward, if I was doing more work, I would definitely want to know what my mesophyll conductance is. To do mesophyll conductance, you have to add a second measurement of chlorophyll fluorescence. It's pretty straightforward to do, but it is not probably negligible if you're trying to do really precise work on what is the CO2 concentration inside the plant and what is the response of photosynthesis to that CO2 concentration. And so, talked about that boundary layer. Just as a quick refresher, that boundary layer is a thickness. It's how thick, how much still air surrounds that leaf, and that's a function of the length of the leaf in the direction of the wind and the wind speed moving across it. And so the faster the wind is, the smaller that boundary layer is, the smaller the leaf, the smaller that boundary layer is. And this is for a leaf that's assumed to be entire, not any sort of unusual leaf. Russ alluded to the aspen are easy. They've got a nice entire leaf. You don't have to have strange boundary layer, what is going on in there. In the 6400, we actually, which is this instrument in front of you, we actually make really precise measurements of the boundary layer, and we know what the boundary layer conductance is, which allows us to make that estimation of what is stomatal conductance. So going back here, we know what this one is, we assume this is negligible, this one is mostly 0, and so we're left with stomata. That's actually how we calculate what is stomatal conductance, which is right here. So when we talk about stomata, we're talking about the major resistance point in CO2 flux into the leaf and water flux out of the leaf. Okay? So in a gas exchange system, such as the 6400, there's several out there. There's Hansa Tech, there's PP Systems, there's Volts, and there's ADC. All of them make photosynthesis systems. All of them operate on that same principle of we know what the conductance here inside the leaf is. We know what the boundary layer is. Whatever's left has got to be stomata. And so that's how we make a measurement of that stomatal conductance. And we know that so if we look at a gradient from low to high for atmospheric CO2 concentration, we see that the leaf conductance actually decreases as atmospheric CO2 concentration increases. So why would that be? Any best guesses? Why would you close your stomata down as the CO2 concentration increases? Yeah, exactly. So you have a photosynthetic rate that you're supporting. And so if the plant could think, the plant would be going, okay, I can still do the same amount of photosynthesis and lose less water. It's a balancing act that is occurring between CO2 uptake and water loss. That is what the stomata are all about, is that they're a balancing act between those two processes. So as we look at the increasing photon flux density, light, we see an increase in stomata. You don't want to do photosynthesis in the dark, it just doesn't happen. And so you need a certain amount of light to drive photosynthesis up to a level. And as you get the stomata open and open to a point, then there's not much point in opening them further because you can't get as much CO2 in because you're actually backing up the CO2 fixing enzymes. You end up with a reduction in capacity and you can't utilize CO2. So that's why you see this plateau. This is where the plant has now not become light limited, it is now CO2 limited. It can't turn over the enzymes fast enough. This is Rubisco limitation right there. So if you look at temperature, plants have an optimum, just like the rest of us. They like to work in a certain temperature. You get too cold or too warm and you don't work quite as well. And they actually, when they don't work quite as well, they close the stomata. The default is closed on stomata. And so this one is gradient and absolute humidity. So I've talked about it a couple times. Everyone know what our relative humidity is, RH? It's relative to what is the total amount that the air can hold at that temperature. And so if you talk about a gradient in the absolute relative humidity, if you've got 100% inside the leaf and 10% in the desert, that's a big gradient in relative humidity. If you're in the southern U.S. or in a tropical region where you've got 100% inside the leaf and the atmospheric is 80%, that's a very small gradient. The stomata are more open where there's a low gradient than they are at a high gradient. The more they're open at a high gradient, the more water they're going to lose, the more they're going to dry out, they're going to die. And so at high gradients, the stomata are more closed than they are at low gradients. And that's going to be important in the 6400 because we actually strip away the boundary layer. And so now this plant is exposed to a different set of relative humidities. And that relative humidity inside the plant is still 100%. And if we strip away the boundary layer, that boundary layer has a resistance. Remember the boundary layer surrounding that leaf has a resistance. And in that resistance, there's a gradient that gets set up from a relative humidity of, let's say, 90% to whatever the atmosphere is. And so there's a gradient in that boundary layer of relative humidity. If you get rid of that, all of a sudden the leaf is exposed to whatever the atmosphere is. And if your atmosphere is 10%, you now have stomata that have been used to seeing 90% because that's the boundary layer right up against them. And you strip that away and give them 10%, what are they going to do? They're going to close. Okay? And so this is probably, for those of you that use 6400s, this is probably the single biggest thing that you can do to improve your measurements, is keep the relative humidity high so this gradient is low, so you're operating at this point in the stomata closure curve instead of this point at the stomata closure curve. And why is that important? Somebody over here said it for me once. So you can get that CO2 inside the leaf and keep your photosynthetic rates up. So just kind of recap on the resistances. We have resistance in the apoplast in the cell. That's the resistance to diffusion through those air spaces. And so how are these conductances calculated? How do we actually make this measurement? So going back in history, in scientific history, photosynthesis was measured in lollipop lenses, and you shine light on it on algal suspensions, and you made an estimate of how much the total gas volume changed. Remember that CO2 is going to be taken up by the plant. It's going to go from gas phase to incorporation within the plant, or plant or algae. They're also giving off water, and so you got an evaporation. So you measured basically a change in the total pressure above an algal suspension is how you actually measured photosynthesis. A lot of work and a lot of errors were associated with that. Then came the advent of infrared gas technology, and it was applied to CO2 and water because those are what people are interested with on plants. And so if you look at the absorption pattern for infrared, CO2 and water have some nice peaks. There's a nice peak of CO2, there's smaller peaks and larger peaks of water. And those are measured by having an infrared source across that wavelength and just measuring it with a detector. And so Hal Mooney and some of his cohort were the first ones to say, these instruments are great, let's take them out and apply it to plant physiology and make these measurements in the field. That is his field portable photosynthesis instrument. Inside there was air conditioning to power the building. He had erga that was a 2 and a bit meter long erga. This one's a 15 centimeter erga. He also had gas conditioning in there. He could control the temperature and the water concentration and the CO2 concentration. That is his field portable lab, and it was field portable. This is taking off down here at Golden, and it was brought up here to Niwot Ridge by air transport, and he actually made measurements up on the ridge. And so this is a whole lot easier. So photosynthesis can now be measured with an instrument. And when you talk about heavy, remember Hal and his motorhome. Okay? So it does have some weight, but it's a whole lot lighter than that big motorhome was. And so how does this work? And so what we have is simply a source. Remember I told you that this is just a heat lamp and a detector? And so here's our heat lamp. It's not as simple as a heat lamp. It's a coil that's controlled at a specific temperature. It's a specific alloy. We know what it is. We know what the spectral output of that is. And we shine that through a cell. A cell is simply a cavity, a tube, a box, a whatever you want to think of it as. And that infrared radiation is absorbed by the CO2 molecules or the water molecules. And what is then passes through the cell is measured by the detector. So we know how much it puts out, how much reaches the detector. The difference in those two is what is absorbed by the CO2 concentration. That is the principle that we use to make measurements of water and CO2. Water we measure about 2.4 micrometers of wavelength. CO2 we actually measure a little longer wavelength. And so what we're doing is we're measuring basically right here for water and right here on the peak for CO2. We're measuring what is the absorption of those molecules at that wavelength. And then the other thing that we do in our instruments is we actually measure just off the peak. And why would that be important? Why would we want to measure just off the peak as well? There are other things in the atmosphere other than water and CO2, and those gases actually do absorb in those wave bands as well. But the other thing is we also have dust, dirt, debris, pollen, other things like that that absorb light in those wavelengths. And so if we look at the difference between what's measured here and what is measured here, the difference between those two is just what is absorbed by CO2. Okay, so this, by measuring just off the peak here and here, we're able to get the baseline, and then we measure the peak and we can calculate the difference. The difference between those two is what is absorbed by the CO2 or by the water at that given wavelength. Okay, and so this is actually a schematic or a cutaway drawing of what's here in front of you. This is the 6400. The ergas are right behind these two gold-plated mirrors, and yes, they are gold-plated. It allows the infrared radiation to be reflected nicely because we fold that path. That's a folded path analyzer. Instead of being 15 centimeters in a straight tube, light comes out of the IR source, is bent twice, and returned back to a detector. And so it makes it a smaller, more compact system. For those of you doing eddy covariance, that same 15 centimeter path length is used in the 7500. Once again, that's a cutaway drawing of that 7500. And we just shine the light in a straight path from source to source to detector. And so we're making a measurement either straight path or bent path, and it gives us the same measurement. Okay? So CO2 absorption. We're going to start with CO2 absorption. We're talking about infrared absorption. And that peak that I showed you, that big tall peak is actually not a single uniform line. If you remember back to physical chemistry and those types of things, there's a bunch of absorption lines. And that's what we're talking about. We're looking here at a bunch of absorption lines. This is, if you integrate this all together, that is that peak that I was showing you. It's a bunch of lines that are together. And those absorption lines have to do with the isotopic composition and the energy of those molecules. Okay, and so C12, C13, C14, all of them have different isotope lines, same thing with the oxygens, and then you give them different energies, and you have the ground state and the excited states for the electrons. All of those things impact where those absorption bands are, each individual absorption band. Now what happens is those absorption bands are sensitive to several things, one of those being pressure. And the reason that pressure has an impact on that is you increase the number of collisions between molecules. As you increase the number of collisions between molecules, you change the energy states and you change those energy bands. And what happens is that peak, instead of being a nice integrated, tends to spread out and shrink. And that's called band broadening. And that band broadening, in an ideal world, we'd have a nice single absorption line. We don't, we've got a bunch of them, formed a nice peak. But as that peak as that gas is subjected to increasing pressure and increasing temperature, they have more collisions between the molecules. Those molecules change their energy states. That tends to spread things out. And then because they're spreading it out, the top peak pulls down. And that band broadening has an impact on what is the apparent gas concentration measured through absorption. Okay, so if you've got a bunch of CO2 molecules, we're talking about nothing but CO2 molecules. They're running into one another. They're causing this band broadening. You need to correct for that. But air is not just CO2. Actually, it's more nitrogen. And so there's an effect of nitrogen, there's an effect of oxygen, there's an effect of everything else in the atmosphere when those molecules collide together. And if you think about what's in the air, the molecules are all different sizes, different shapes, different conformations, and they're going to have a whole collection of energies. And as those molecules collide with CO2, they interact differently. And so there's an effect of oxygen, there's an effect of nitrogen, there's an effect of water, and all of those need to be taken into account when doing CO2 measurements. Okay, and so that's that band broadening is what we're going to refer to that as, and there is a band broadening correction. So our analyzers are corrected for the band broadening effects. And the nice thing is that if your gas concentration stays relatively stable, let's pick on nitrogen. So the nitrogen effect on CO2 is going to be about the same across the board. And the reason is the change in nitrogen when you're making measurements of photosynthesis is tiny, negligible. It doesn't exist. And so the effect of nitrogen on the gas when there's no photosynthesis occurring and when there's photosynthesis occurring doesn't matter. That change in the partial pressure of nitrogen across the board is, you don't even see it. It can't be corrected. Same thing for oxygen. The oxygen concentration, while the plant is producing some oxygen, you're adding a few parts per million or less to a background of 21%. So the addition of those few ppm to a background of that large doesn't really have an effect that you can calculate and measure on CO2 analyzers. Now water does. So you've got water that comes out of the leaf, has a huge impact on what's going on inside that gas volume that we're trying to measure with CO2. And so we do need to correct for the water. Okay? And how we do that, so we have a concentration here, we have a Lycor function. That's all that is. That's a function that Lycor does. Every analyzer is different. Every analyzer has its own function. I'm sorry, analyzer set. So 6400, 7500, 7000, the families have their own functions. And it's a function of the pressure. So we have ideal pressure, and then what is the current pressures, and then we also have a volume. So remember ideal gas law, PV and RT. We're dealing with the P and the V and the T here. Because as the pressure increases or the temperature increase, if you got a finite volume, volume's not getting any bigger. And so if the temperature increases, we're going to increase the pressure, things are going to collide more, and those collisions are what we need to account for in that band broadening, that as those absorption lines start to spread out and the peaks pull down. Okay? Make sense? You with me? All right. So we talked about gases, talked about different size gases. Not all of them respond the same, and the standard is that we normalize back to nitrogen. So what is the partial pressure of the nitrogen? Then the sum of everything else that's going on. So this is all the other gases that are in there. Argon, water, oxygen, on down the list. And then there's also this effect of CO2 on itself. As you put more CO2 molecules in, you're going to have more collisions between CO2 molecules. If you pump in more, you're going to have more, and so there's a self-perpetuating, and there's an effect of CO2 upon itself when we actually account for that. So if you think about it this way, when we're doing photosynthesis response curves, we make measurements of 400 parts per million CO2. We make measurements at 1600 parts per million CO2. There's going to be more collisions between CO2s at the high concentration than there is at the low concentration. And that's corrected for in this band broadening that we actually correct for. So the total partial, this is the effective partial pressure. And so that's the effect of all the gases upon what is the apparent concentration of CO2. Is this effective, you can look at this also as the effective CO2 partial pressure in this instance. And that's the sum of the nitrogen effect, the oxygen effect, the water, and the CO2 upon itself. Okay. Make sense? And so from there, we now are able to plug that in. We have a couple of terms. We have the temperatures, we have a flow, and then we're able to calculate what is that CO2 concentration. So, now that we've made a measurement of what is the CO2 concentration, or we make the same thing for water, how do we make those measurements? Well, there's a couple of big schools of thought. One of them is we put a box around things and make a measurement. The other one is we make a measurement of what's going on and live with the variation. Those are really the two big classes that we have of making measurements. And so the enclosure method has some limitations. They do cause disturbances. They impact the plants. I don't care what kind of box you have, it is going to have an effect on the plant. We have the possibility of controlling that box though. So if I want different concentrations, I can control what's inside that box. We also can make measurements of components. So if you have little bitty boxes, great big boxes, but you can compartmentalize different things. Whereas with micromet, you have minimum disturbance. You're not really impacting the system that you're trying to measure. There's a little bit of heat transfer in a few things, but for the most part, that's negligible. Problem is, though, you have to summarize over fairly large areas. You can't compartmentalize and say, this leaf is doing this. And so it's limited in that way. And then it's also almost impossible to do any sort of controlled environment. I want to change the CO2 concentration. I want to change the temperature. They can be done, but they're much, much more difficult than if you have a box and want to change those conditions. Okay? And so we're going to talk about the box measures. And there's two ways of doing boxes. You can have a box, you put it over whatever you're interested in, and then measure what happens in that box over time. And that box is completely sealed. And so everything going on in there is due to whatever you sealed up inside the box. And that's called a closed system. The other alternative is you got a box, you put something inside it, and you flow air through that system, and you keep things at a constant condition. By whatever's being added, you take it out. And so there's an open system. And this is what the 6400 in front of you operates on. If anyone's ever used the old 6200, it was a precursor to this instrument. That was a closed system. And so both of those will give you the same set of measurements, the same flux. We still get photosynthesis, but the calculation is slightly different. Inside this closed box, you need to know how big your box is, how much the gas of interest changed, and then how long it took for that change to happen. Okay? So you have time, you have a volume and a delta, a CO2 change. In an open system, you have that same CO2 change. So you have CE entering, CO2 going out. So you have a delta. You have a flow rate. And that flow rate is a measurement of air in time. So you got your time back in there again. And then you're able to calculate, both of these have S. That is leaf area. That S is the normalization to leaf area. And so in a closed system, no air enters or leaves. It's a sealed system. But the problem is that you've got a transient measurement. You know, photosynthesis responds to CO2 concentration. We're going to see that this afternoon. We're going to measure that. And that change in CO2 concentration inside a sealed box impacts the photosynthesis rate. And so as the CO2 concentration rate goes down, the photosynthesis rate goes down. And that time that you measure over is an average of what was the rate between the beginning and the end. You're getting an average rate. You're not getting it instantaneously. What is my rate at 400 parts per million CO2? Whereas an open system lets you do a steady state measurement. With a steady state measurement, you can control exactly at 400 parts per million CO2 inside that box, and what is my photosynthetic rate at that concentration. Now its limitation is, because you have a leaky box, you have a problem in measuring very, very small changes. So if you've got a very, very small flux, it's better to have a closed system. With a closed system, you just clamp onto whatever you're looking at and leave it there until you've got a change that you can measure. If you got an open system, your lowest flow rate, how slow you can pass air through that system, defines the smallest amount of flux that you can measure. So that they both have their limitations, both have their strengths. So in the 6400, we have a set of variables that we measure. We measure CO2, light, flow rate, water, and temperature. And why are all of those important? I gave you most of the answers early. CO2, why do we want to know CO2? We want to calculate what's the CO2 flux, what's the photosynthesis. Same thing with water. We calculate what is the transpiration rate. Why do we need this flow rate? Well, it's that what allows us to calculate what has been entering the chamber, and it's that time constant. So if you've got a slug of air that moves from outside through the box and then out, if you measure it before and after, you know what happened inside the box. And that's what an open system does, is we have a slug of air that we measure. We know how fast it's moving through. We know what the CO2 concentration entering, the water concentration entering, and we know what the flow rate going out, the water concentration out, CO2 concentration out, and we know what happened inside the box. Now, in a gas exchange system, the flow going from the green box, which is the console, through the tubes and out is not the only thing that's affecting what's going on inside the chamber as far as gases. What else is going on inside there is you have photosynthesis going into the leaf. So CO2 is going from gas phase to a liquid phase, dissolved, and then it actually becomes fixed in solid phase when it is fixed by the Calvin cycle enzymes. You also have E, transpiration. Water is coming out of that. It enters the chamber through the petiole, through the leaf, in the liquid phase, and then it evaporates to the gas phase. And so we actually have to account for what is that evapotranspiration addition to the chamber. Because this chamber is not a black hole. You can't just have mass go and not come out. And so what we do is we actually know what the evapotranspiration rate is, what the flow rate in is, and everything going in has to come back out. And so one of the assumptions we make is everything in through the mu and the E is equal to what is coming out. Okay? Make sense? Okay. So here's our assumptions. First one you just pointed out. We assume everything going in is everything going out. Okay? We also assume that the interior of the leaf is saturated. That airspace is saturated. We assume that. That's a pretty solid assumption. It tends to break down when the leaf is crunchy. When a leaf starts to senesce, they lose control of the aquaporins that control the water loss out of the plasmalemma. And so the interior leaf, even on a yellow leaf, is still 100% saturated at that temperature. We assume conductance through the cuticle is negligible. There's not really anything measurable going through there. We assume that we know what the boundary layer is. And we assume that there is a difference between CO2 conductance for water and CO2. Why would that be? Why would there be a difference on how those molecules move through air? Exactly. Molecular weight. You've got a small one and a big one. The small one moves easier. And that's what it has to do with. So here's the calculation. We're actually measuring the flow rate in. We have the transpiration rate here. We have water out, water entering. The difference between those waters and the flow rate lets us calculate what is the transpiration rate. We solve for E, and that S right there is leaf area. Okay, so we have water difference, and then this is the correction for the water entering the chamber. We have to add that back in. And so this bottom is essentially for the water entering the chamber through transpiration. So from there we actually calculate what is the stomatal conductance. Stomatal conductance, remember we talked about resistances being additive, and so we know that the total conductance is a reciprocal of the total resistance. So if we know what the water in the leaf is, the water exiting the chamber, why did we switch nomenclature there? This is the water entering, water out. We can actually calculate what is the total conductance with those assumptions we made earlier. that we know what the boundary layer is, we assume that the cuticle is negligible, and we're not worrying about mesophyll, we're able to solve for the stomatal conductance to water, this guy here, okay, because we know what this is and we know what the total is, so we're left with stomata. And this KF has to do with where the stomata. So if you have 50-50 distribution, you've got the same amount of conductance out of both sides of the leaf. Plants aren't normally like that. They have about 2/3 on the bottom, 1/3 on top. And so you need to account for that in the distribution. And this goes back to what Paul pointed out, that as that boundary layer changes, you have actually a change in what's the conductance through there, and you need to account for that because these two are working in parallel. The conductance out of the top side of the leaf is working in parallel with the conductance out of the bottom side of the leaf, and you need to proportion that accordingly. Now, having gone through a long explanation, the effect is actually pretty small on the total calculation, but it is real, and that kind of what Paul was talking about was anything that's working in parallel needs to be accounted for, and that's what this correction factor is. So, photosynthesis, very much like the transpiration measurement that we make, we actually account for transpiration. Remember, we talked about band broadening, effect of water on CO2. We need to correct for that. That happens right here. We're increasing the pressure inside the chamber by adding more water. And so we actually correct for that. There's that transpiration. That's why transpiration shows up in the photosynthesis calculation. We solve it for A. We have the flow rate entering the chamber. I've changed nomenclature here. This is the first time I'm going to introduce R and S. Those stand for my reference analyzer and my sample analyzer. And those two are important because the reference measures what's going into the chamber, the sample measures what's in the chamber. The difference between those two has to be what leaves the chamber. Okay? And so how it leaves the chamber is typically in photosynthesis. We have the transpiration rate. You see CS is here. That CS, the transpiration rate, is only applied to the CO2 concentration inside the box. So we have CO2 concentrations that are being affected by what's going on with water being added to the box. We apply that correction to what's going on inside the box. So I'm going to take us to a little walk. Shannon alluded to it earlier, where we actually talk about the difference between CO2 diffusion within the leaf, apoplastic volume, CO2 diffusion in the atmosphere, and CO2 diffusion through the stomata. And so we actually calculate what is the intercellular CO2 concentration, CI. This is going to be important. You're going to do ACI modeling tomorrow with Carl. And we need to know what is that CI. How do we measure what is the CO2 concentration inside a leaf? Well, we can't. We have small analyzers, but they're not that small. We've got to make some estimates, and how we make that estimate has a fair number of assumptions. And this is going to be important because a phone call we frequently get is, I've got negative CIs. Can you have a negative CO2 concentration? Just physically not possible. You can have 0. You can have no CO2, but you can't have minus 400 parts per million CO2. It just doesn't work. And what happens is the math goes, for lack of a better word, it goes wonky. And what happens is the errors have accumulated to a point that you're dividing by a fairly large number. You're dividing a very small number by a very large number. And so what happens is we make an estimate of the stomatal conductance to CO2. How we make that estimate is we remember reciprocal, so CO2 reciprocal conductance. We make an estimate based on what is the stomatal conductance to water, and we have that 1.6, okay? And so if you look at that flux, going back to that early flux fixed first law of diffusion, if we know what the photosynthesis rate is, remember I showed you how we calculated that earlier. If we know what the resistance to CO2 is, and we know what the CO2 concentration outside the leaf is, we got one variable to solve for, CI. That's what we do. We actually solve this thing for the CI. But there's some problems in there, and this is where Shannon was talking about. That total conductance is actually not the 1.6. So we have 1.6 in the boundary layer. In the stomata, because water being a sticky molecule, it adheres to things, and it changes what's the diffusion ratio between water and CO2. So we actually account for that. Here's that accounting for the difference in the diffusion coefficient for water within the throat of the stomata versus the water within the bulk atmosphere. And so that's where that 1.6 versus 1.3 that Shannon was talking about earlier comes in, is in the estimate of the total conductance. Remember, we take that total conductance and we say, okay, we know what the boundary layer is, we're ignoring the cuticle, the remainder's got to be stomata and water. We know what the ratio between stomata and water are, and we can calculate back to that CI. Okay? And so there's some assumptions that go on, and that's something as you're doing these curves you need to pay attention to. I'm not going to talk about where people use this. You know better than I do about different uses for leaf level measurements, what you want to do with them. Do you want to look at them for leaf level? Do you want to take them, scale them up? How you're going to scale them up? There's lots of things that you can do. Lots of things people measure. Net photosynthesis, what's just going on at the moment. Transpiration and conductance. Intercellular CO2 concentration. Then you can get into wild things like the electron transport rate. If you use chlorophyll fluorescence, you can measure how fast electrons are transported through photosystem 1 into photosystem 2. Actually, it'd be the other direction, photosystem 2 into photosystem 1. Through the B6F complex to drive the ATP synthase, to make the energy for the carbon cycle. You can measure all of that with these portable field photosynthesis instruments. And Carl's going to show you how to model the velocity of carboxylation tomorrow. That's a measurement of rubisco, how fast that rubisco turns over and fixes CO2. So if you haven't read this paper and you have any interest in gas exchange, look up Long and Bernanke. It's a really good summary paper. This is the response that we're going to shoot for today. Depends on how good we are and whether we get it. So we're going to look at the increasing CO2 concentration and the photosynthetic rate. The nice thing is, based on Farquhar, von Kamer, and Berry's work, photosynthesis is the minimum of 3 different processes. The rubisco limited portion of photosynthesis, that's the initial portion of that curve. Rubisco rate controls that portion of the response. The next portion of the response is RUBP regeneration. This is a measurement of how fast you can turn the rest of the Calvin cycle to get your RUBP back, to be ready to fix another CO2, and it's a measurement of how fast the electrons are being transported from the light gathering, from the light reactions to the dark reactions. And this last one, modification by Sharkey, that is the triose phosphate utilization. That's how fast the triose phosphates are being shunted out through the antiporter with the phosphate back into the chloroplast, so that they work in opposite directions. Triose phosphate out, phosphate in to the chloroplast, and that's controlled by a single antiporter. And that's the last portion. Typically, we won't see that sort of limitations. In C3 plants, when it is found, it's found at like 1,600 parts per million CO2 and above. So it's very high CO2 concentrations. So light, we talked about controls photosynthesis, controls stomata. We're talking specifically about photosynthetically active radiation, the 400 to 700 nanometer wavelength. When we turn these on, you're going to see that they're red and blue. And so that red and blue are absorbed principally within the plant. The green is not absorbed so much. Plants reflect green light. So greens aren't used typically in photosynthesis systems. You don't see green lights. Same thing as a CO2 response curve. As light increases, photosynthesis increases, and this is some of Shannon's data. Yeah. I forget what it is exactly. Was it wheat? But so you see an increase. And so this initial portion of the light response curve is the light limited portion of the curve. Up here at the top, we flatten out, no longer light limited. You're actually now limited by rubisco. Okay. So I promised you the flow path. We have about 2 more slides and we're done. And so this is the flow path. This is the green box. This is that silver head sitting out in front of you. What happens is we actually pull air from the inside. We condition that with a CO2 scrubber and a desiccant we control the CO2 concentration to 0 if we're using the CO2 injector. We control the water concentration to a range, and then we flow it into a CO2 flow control. So we take out all the CO2 and then we add CO2 back into whatever concentration you want. The reason we do that is it's nice to have a stable number to work from. Engineers like nice, uniform things that they don't have to guess. They could have chosen any number. The easy one to control is get rid of all of it and then add it back in. And so that's how the system works. We control CO2 by scrubbing it all out and then adding back in whatever you want. We have a pump that pulls the air through the system, or pulls on this side, pushes on this side. Then it runs through the mass flow controller. We have a single mass flow controller. It's located inside the console. Then we shunt that out to a flow diverter. This is your flow control. They split that. We split it again, and there is your mass flow controller. So we measure only the sample line. We don't care how much air goes through the reference, as long as it's getting the same air. And so the only one we need to know is what's going into the box. That's that flow controller there. Then there's 2 tubes exiting the side of the green box. Those go up to the head. We have 2 analyzers. We have a sample analyzer and we have a reference analyzer, and those are separated. So once we split it down here, that airstream is same airstream, then we split it in half and we assume that there is no changes, impacts on that airstream, okay, until it gets to the leaf. Now, our system's a little different in that we have the analyzers up here at the head. Other ones have it in the console. They have to run the gas out and back to the system. And so that makes a longer response time of the system, a little bit slower. And then we have a common exhaust. And that's actually a really important little feature where the airstreams come back together and then leave the system. And the reason that happens is, remember, we talked about band broadening and the effect of pressure. If we have one analyzer at one pressure and the other one at a higher pressure, then those 2 analyzers, even if they're seeing the exact same CO2 concentration, are going to tell you that they're different because of the effect of pressure. Okay, so if you're given both of those analyzers, one at low pressure, one at high pressure, 400 parts per million CO2, the one at low pressure read 400, this one may read 410. Actually probably be closer like 402, but that would be 2 ppm different, and that would be calculated into your photosynthetic rate, and that would be an error. And so if they have a common exhaust, they have to be at the same pressure. Pressure works that way. You come into a single port, and they're going to be the same. And so we keep those 2 analyzers at the exact same pressure, and so we don't have an effect of pressure. We don't have to measure pressure inside the analyzer. This is a cutaway of what's sitting in front of you. You can see right here the detectors, or back here the IR source is on the other side behind what you're looking at there. This is the flow path, this is the sample erga, this is the reference erga, and the sample erga shares the air volume with the leaf chamber. So it's the same air volume. Somebody asked me earlier about the mixing and what's coming into the chamber and what's being mixed. And so this fan right here is mixing this system very, very quickly. Lots of turnover, lots of airflow. That's what controls the boundary layer. And you can see the flow path here. We're blowing air up into the system and out, and then we drop back down in. And so that air is constantly being mixed and turned over. And that mixing rate is much faster than what is entering the chamber. And so I told you about the infrared absorption and how we measure on the peak and just off the peak. And we do that through a little clever thing that one of the engineers came up with many years ago. Simply a wheel. Has 4 filters on it. They turning 300 times a second. So that's turning very quickly. We measure on a peak and we measure just off a peak. We measure on a peak and just off a peak. And we calculate that difference for each one of those concentrations on each one of those analyzers 300 times a second. It's actually fast enough you could do eddy covariance with it. And with that, let's take a break.